Hi everyone. I think we can start now. So welcome to the fifth and final day of this workshop. Thanks to all of you for making it through the week and attending the last day. So today we're going to try and bring together some of the threads that have been brought up throughout the whole week and sort of collate it and bring it together under the heading of community resources and efforts. So what plans and tools we can put together as a community to answer some of the questions that have been brought up over the last few days. And so let's go to the next slide, Cecilia. So we've broadly grouped the discussion we're expecting to have into three sections. So the first is community efforts on data and follow-up and sharing of data. The second is on modeling frameworks, the currently available software, what software we would like and what software we need, and also how we can test our models in a controlled way, and a controlled and uniform way across different modeling approaches. And the final topic is simulations, and then generating mock catalogs from those simulations. So what are the most sophisticated simulations we need to answer some of the questions that we're interested in, and how can we then use those simulations to understand what we're observing. And so we had a nice bunch of talks submitted under these sort of broad headings. So we'll go into more detail on those later, but we heard about several survey efforts, broad sort of photometric surveys like from the various DECAM surveys, and then also spectroscopic efforts like forthcoming Foremost survey, as well as the much more focused streams dedicated survey, S5, delivered by Ting Li. And then also efforts for trying to understand and characterize and discover streams around other galaxies. So Alejandro Borlaf gave a nice talk about that. And then we also heard from Heidi Newberg on Milky Way at Home, part of a modeling effort, and then Andy Everall on characterizing Gaia's behavior. And then finally, a nice talk from Ethan Nadler on sort of tailored Milky Way simulations. So I'll hand over to Cecilia, who will go over some of the questions and some of the ideas we have about how we can improve community efforts towards data collecting and data sharing.
Yes. Thanks, Jason. So yes, in this topic, we're going to summarize some of the things that both we had thought about and that came up during the week on the broad topic of surveys and the data that's going to come out of those surveys and the current available surveys. So, and how to share them and store them and make them available for the broader community. So this was a topic in which we grouped these many ideas during the week, some of which we're listing here. And we're going to start just with a very quick overview of some of the facilities that are coming up. And this is motivated by desire to summarize what we already know, but also to get a jump ahead on whether we have facilities planned that will capture all the data we want. Of course, a lot of the discussion during the week went around whether we know what kind of data we want, and that's going to depend on, of course, the science questions that we're going to address. And well, So we came, I think, to the global conclusion that to model multiple streams, we need data for multiple streams, but then we also need to be able to access that. So this is where the data repositories are going to come in, and possible databases to store information for streams, actual stars, and metadata for streams, and meta catalogs with summary data that can allow us to know whether where's the stream in the sky, what's its proper motion, its schematic signature, and so on. And also, well, with the available data, can we share target lists, or a place where we can summarize target lists for follow-up, for mid-scale surveys, both that are planned and that are going to be coming up, and that we don't have too many redundancies, so that we can coordinate efforts for follow-up on different streams. So this is a very quick summary of some of the surveys that are planned or ongoing already in the Milky Way. Tingley has a very nice talk that Jason also already mentioned on the S5 survey that's doing spectroscopic follow-up of stars, mostly giants, in streams in the southern hemisphere. They started with DES streams, the streams that were identified in the DES survey, mostly around the Magellanic Clouds, but they've expanded already. And so go and check Ting's talk if you haven't already, and the thread in the Slack discussion for more details on this. Also, and closely related to this, actually, it's Alex Wagner's talk on the dark energy survey and DELV, which, let me remember what it stands for. So it's the DECAM Local Volume Survey, which is an ongoing effort to combine new observations with archival data to cover the full southern hemisphere with deep GRSCY photometry. And it will have some dedicated areas in the LMC and SMC survey, and also on some nearby galaxies that are going to go deeper. And so go and check Alex's talk for more detail on this. And we've already seen how useful DS data has been in revealing many streams. So we have lots of hopes for this. And also it serves as a sort of setup for, or preparation for LSST because of the depth and the kind of data that it's acquiring. Rolf de Jong also submitted very kindly a last-minute talk on PROMOST that was very focused on our interests for galactic archaeology. So go ahead and look at that if you want more details. This is going to be a spectroscopic survey with both low-res and high-res versions. And there are a bunch of slides on other streams, other surveys, sorry, like MegaMapper, the Mauna Kea Spectroscopic Explorer, Rubin or LSST, that were kindly provided during these days. These are all linked on the Indico page, so go ahead and look at these. So this is by no means a complete or exhaustive list, I think, on the facilities that are coming up. So this is just to give a panorama of some of them, but we can make perhaps something like a resource to summarize this kind of thing, perhaps in the running notes or somewhere else. There are also going to be facilities that are going to be focused on going beyond the Milky Way. There's a very nice talk by Alejandro Borla on Euclid that's going to do it's going to be very useful for very low surface brightness targets. And it's going to go down to surface brightness of about 29.5 magnitudes per arc second in a very large area. And it's going to have smaller surveys with even deeper reach. and it's going to build on experience developed with HST. So this is going to be amazing for studying streams and other shells and features like that on numerous samples on galaxies beyond the Milky Way, something that we talked about extensively yesterday, and that will be very useful for different science questions, complementary to those that we have in the Milky Way. And I didn't mention it, but it was also on the previous slide. This is the prime focused spectrograph with the SURU, and also the Roman mission that we've talked about a lot these days. So this is clearly an amazing set of both coming and current surveys. So one of the questions is, what kind of data are we missing? For example, something that I'm not sure came up a lot during this week, but was mentioned, I think, a couple times. How are we doing on UV photometry once HST is going to be dead? So are we going to need that? Are there any other gaps in coverage? So to go a bit faster on this, well, these are the facilities, but then we're going to also need, and it's probably going to be very beneficial for the community to have data repositories. So here we've split them into basically two kinds, what I call the actual stars repositories and the metadata repositories. So something like the Open Fast Stars catalog repository of hypervelocity stars, where you have data for actual stars that you can go and follow up. And once you have rate of velocities or chemical data and so on, you can submit it to the database and the community can access that. And so it would be a way to keep track of what stars have already been observed and avoid a lot of redundancies and try to get more completeness. And then there are the other type of repositories, like the Gauss streams that I run, which are more on metadata. So where are the streams? What are the streams tracks in the sky, in coming up in distances, proper motions, rate of velocities, so that when you identify something new, you have somewhere where there's centralized data and you go and see there's something already known in that area of the sky and with a similar kinematical signature, or that you can use that to try and to fish out information and do follow-up and characterization on known streams that are lacking deeper photometry or rate of velocities or proper motions, kinematics, and so on. So these should be very useful for the community. And we have examples on how to do this from other communities, like the exoplanet one. So have a look at the ExoPub webpage here. And this would be something that could inspire us to try something like this in our own community. So I think I can already pass on back to Jason, who's going to talk on the modeling frameworks, software testing suites.
Yep, thanks, Cecilia. So yeah, we'll go to the first slide. So yeah, just a few slides about sort of common efforts towards modeling frameworks. So one of the things that's been raised over the last few days is maybe a concern that are we in a good position to be able to automatically model many streams, so not just around the Milky Way, but potentially around many external galaxies. And so are the tools currently available for doing that modeling on a large automated scale? And another question here is, are we even sure what quantities we want to measure? Do we have the right set of summary quantities we want to extract from any modeling effort? And then what should be reported and shared by these efforts to enable comparison between different studies? Over the last few years, various Python and C++, I suppose, packages have done great service to the Milky Way and dynamics community. So GalPy, Gala, and Gamma, and in particular, they're providing just a default Milky Way potential that somebody can easily pick up and run orbits in. So this has been particularly valuable in light of Gaia data. Do we now want to have a sort of standardized Milky Way plus model to then share outside the community, so people are using some sort of standardized models there? And then there are these three great packages, but is there scope for combining the best of all of them, and sort of which packages excel in which areas, and can we take and draw on those various strengths to build something that's, I suppose, better than just the independent sum of them? And so on this same point, are the methods and routines that are being run sufficiently standardized, such that we can imagine them being incorporated in a fairly standard way that people can agree on? And this kind of effort, it obviously requires a significant amount of work, but on the flip side, it minimizes duplication of efforts, and also it becomes a kind of one-stop shop then for people to implement new things into their into this framework. So I have the next slide. And so we heard about some of these modeling frameworks in the talk. So Heidi gave a very nice talk on the Milky Way at Home project, which now is a sufficiently flexible framework that you can run collisionless or collisional n-body simulations inside custom potentials. And so, yeah, there's a screenshot from her talk there. So yeah, if you haven't seen that, I think it's only a minute video. So yeah, should check that out. And then other more sort of just dynamics packages that I've just mentioned, GalPy, Gamma, and Gala, and then AMUSE, which is a sort of framework to interface between different modules. And I think later there's a plan to have a kind of mini breakout on AMUSE. I think Jeremy Webb and Eugene and somebody else who I've forgotten were keen to set up. And then also yesterday was some talk of kind of more citizen science or machine learning driven approaches, such as the stream zoo. So is this the necessary modeling framework we need going forwards for modeling this huge number of streams? And then we also heard in the talks from Andy Everall on characterizing the behavior of Gaia. So that Gaia is essentially how Gaia, what Gaia's errors should be, and how we can then understand and use that information. And so this is all essential work, the characterization of the instruments and how we can then use those sort of instrument models in our modeling. And then finally, I think finally the next slide. Oh no, there's two more. Yeah, so on the subject of how we report and share modeling results. So I've heard a bit recently, I think Dennis Urkel was talking about this, that Paul Macmillan for his potential fits provides Monte Carlo samples, which are very useful then for iterating over many different potential realizations to understand the uncertainties in orbits, pericenter calculations, for instance. And these kind of Monte Carlo samples or constraints are also important for constraining potential models in other analyses. However, it becomes awkward because there's no common parameterization. And so one thing that's been brought up a little bit is, what would a common potential format, a standard Milky Way model look like? Is this basis function expansion plus a Milky Way LMC orbit combined? And are we in a position to just standardize what that looks like? And then one idea is, kind of drawing a bit from the cosmology community. So I was looking a bit at this cosmosis work from Joe Zuntz, and how how people commit sort of likelihood functions to that package, so people can turn on and off different data sets, different likelihood functions, to then look at combining different constraints from many data sets. And so, whether that's the kind of way forward, we should be thinking about how we can combine all the constraints that we're getting into a uniform framework. And so now I think the final slide that I was going to talk on, and how we test our code. So one great success from a number of years ago, ran 2013 to 2019, was the Gaia Challenge. So designed in preparation for the Gaia data and to enable testing of modeling codes. And there was a streams subgroup within that many of us attended and participated in. And I suppose some of these efforts sort of fizzled out a bit, and why did that happen? How can we make working on these kind of things attractive? And also, what are the new, if a Gaia challenge happened now, what are the new test sets that we would define? For instance, these test sets were all generated when in the sort of good old days where we didn't worry about the LMC very much. And so, now is that should be a part of any test set. And then finally, one thing that's been brought up this week in some of the breakouts are blind modeling challenges, which I think the Gaia challenge never went that far, but these have been very influential in other fields. So that's all I had to say, I think, on my part, and I think I'm handing over to Adrian.
Sure. Okay, started us off. Yeah, so I was going to talk about the third theme here, so on simulations and mock data sets generated from simulations. So there's a lot more to say here, and perhaps because we called the meeting Streams 21 and wanted to focus more on streams, there's not as many simulation style talks or contributions, but I think there has still been a ton of discussion around like what we need from simulations and what we need to improve our simulations of streams. So one of these major themes, I think, is something that came up almost every day in different contexts, which is that there's clearly a need for simulating streams in more realistic simulations, and realistic can mean different things. It can mean having a more a proper cosmological history or growth history or merger history in the galaxy that you're simulating, or want to simulate the streams in. It can mean more specific things like being able to simulate an LMC Milky Way interaction and then inject streams using force playback as a way, with basis function expansions as a way to better capturize the time evolution of the overall dark matter distribution. Or it could mean something like better capturing aspects of simulations like fire or hydrodynamic simulations that have more realistic baryonic perturbers like giant molecular clouds. Related to that, but slightly different, I guess, is the need for returning to this point that many of us use particle spray or mock stream methods to very quickly generate streams and compare it to data. But I think there is still a need to run more realistic, sort of state-of-the-art globular cluster simulations that disrupt with n-body 6 or whatever, and then do more appropriate comparisons of these types of simulations with the mock streams. And this is something that people like Mark Fardal and Dennis have looked at, but I think not in the context of having a library of n-body 6 simulations and more realistic potentials, for example. And then, of course, a third thing that's very, a third thing that's very important and connected to all of this is once you run the simulations, we need to be able to quickly generate mock data sets with realistic survey selections, and that's crucial for interpreting what we actually see in the surveys and our completeness and things like that. Okay, sorry, go to the next one. So what do we have now? There's a really interesting teaser talk from Ethan Nadler about the Milky Way Est simulation suite. And I think we now have simulations that span from Milky Way-ish through Milky Way Est. And so the Ist here means that they tried to match the accretion history as closely as possible for the Milky Way host. And so that clearly has a lot of legacy value and will be really interesting to try to analyze in the context of streams. There's obviously many other types of simulations from FIRE and Latte to Auriga, et cetera, and then equivalent mock data sets generated from them. And so I guess a question to ponder is, we have all of these simulation suites, let's rerun or do force playback with injected stream progenitors and start comparing some of the goals that we had from the previous slide. Okay, next one. And then there's a whole bunch of other topics that either came up in the notes or were suggested in the initial registration form. So I won't go through all of these, but let's see. So I think there's possibly some technical solutions to some of the questions or themes that came up on the previous slides, like AMUSE, for example, might be a good framework for marrying the simulations at very different dynamic ranges. But I think another thing that has come up is that we clearly need more tutorial material or sort of field-specific demonstrations of how to do this kind of thing with AMUSE, since the sort of soup to nuts getting up and running with AMUSE is clearly a bit more difficult than just generating a mock stellar stream in GalPy or Gala or whatever. Yeah, so there's some other topics here. I don't need to go through them all. I think these are just to get you thinking about the types of things we want to be discussing in the breakout sessions that we have. So I think we can carry on. Oh, I guess this was me. So this is not necessarily a fourth sort of global theme, but this is something that I do think is important to think about and for us to discuss and think about in the context of all of the things that we've talked about this week, which is related to the sort of community and the culture that we have in our subfield. And so I think another sort of meta topic that came up is this desire to have more standardized sets of measurements or standardized tests of our methods, sort of stricter or more rigorous analysis or comparisons of analysis. So how do we go in that direction while at the same time sort of preserving the Wild West fun discovery aspects of streams and Milky Way science? There's another topic that has come up in various contexts. There's been some Twitter discussion about this. Naming, so this is a big topic, and it'll be difficult to discuss this amongst the whole group, but naming streams and substructures, obviously right now it's a total mess. And so there's some question about whether we want to try to organize as a community to get ahead of someone else like the IAU trying to impose something on us by collecting a set of recommendations to give to the IAU as what we want to happen. And so hopefully we won't end up in a streaming extreme face situation. Although I'm sure Vasily has already considered naming streams something like that. And then the last thing is related to everything Cecilia mentioned, which is if we're going to be sharing data, coordinating follow-up, if we're going to be sharing our software and having shared test suites for the methods that we have, if we're going to be sharing simulations and mock data sets, do we want a community-wide MOU or sort of statement of community practices that we want people to agree to if they're going to be plugging into all of these things that we provide to everyone else? Something, food for thought. So that's all I had.
Okay, thanks, Adrian. So we can pause briefly if people want to just comment on any of the points raised, or we can just proceed as we've spoken for a fair amount of time.
Yeah, apparently the organizers are the worst at time management, so it's a good thing we identified so many good moderators throughout the week.
Okay, so I think we're going to stick with the usual format of going into random breakout rooms, and so some things just to think about and discuss in your groups. What tools and projects would help your research over the next 5 years, and how can you do something about making that happen? So, and then we plan on later coming back and talking in bigger groups on those 3 main headings on data modeling and simulation efforts.
Okay, so let's go with room breakout recaps. Does anyone want to volunteer to share what you discussed?
Yeah, I'm happy to go first, just while I still remember it. We kind of talked a little bit, this is breakout room 9. We kind of talked about all 3, what we were looking for in the near future for all 3 bits that we were curious about, which is the data, the modeling, and simulation efforts. For data, we said that we wanted a place where we wanted 2 things. One was that we wanted a place for each stream that says, here's every paper that lists this stream and its work. And so if you say, I want to know what the work on the OL stream is, then you can go there and you can say, oh, look, these 10 papers all do work on the OL stream. And we kind of realized that's a little bit of what Gal Streams is doing. And so thank you, Cecilia, for the work there. But there's also things like Simbad, which kind of scrape papers for that data, and kind of marrying the efforts of those 2 would be a good step in the right direction. Just saying, hey, look, I did work on this stream. Let's kick it up to some GitHub repository and say, we can have this collection of those. And then also pushing to do publication of individual stream members in papers. So if you did work on a stream and you have candidate members, and then you should publish that for other people to look for, so that people who are going through and scraping this data don't have a huge hard time in order to do that. The next thing for modeling that we wanted was we were looking for an easy way to kind of share potentials, whether that's basis function expansion or some other method of easily sharing things like coefficients or information. That would be beneficial, because right now it's a bit of a Wild West situation with what potential are you using? How does that relate to other people's work? And I think we're starting to get there, but it can definitely be improved. And the last thing was that we really wanted good, realistic mocks of the Milky Way. So things like you can go and look at a mock simulation and say, here's what the background would look like, here's what the streams would look like. These are kind of realistic expectations of how many cold versus warm streams you would have, how many globular clusters versus dwarf streams, etc. And that would also be beneficial for a lot of people.
Great, Tom. Guillaume rose his hand on the chat, and perhaps we can go next with Orlin.
So I'm going to resume the discussion that we get on Breakout 3. So we get different discussion. One of them was about, this kind of catalogs data sets. And I think that at the end we converge that we need 2 different catalogs data set. One which is on where are the streams, so a catalog of streams basically, as you did, Cecilia, for Gal Stream. But we think it is a kind of unfair to just give that to someone which is not paid. So maybe it should be a community effort to do that. Maybe forcing us as well to meet every year to know what is a stream, what is just a candidate. And these catalogs, again, are going to be really useful in general for us as a community, even for the candidate, because it can lead to some people to say, oh, we need to get some follow-up observation to be sure it is streams. So it's useful to keep the candidates. But also I was mentioning for extragalactic people, because personally I've been contacted by extragalactic people to know where is the stream, because they need to basically put the telescope outside this area, especially for Sagittarius. So anyway, it's good not only for us, but for a lot of people, but also for planning large surveys, for example. It's nice to get maximize the number of streams that you have. The second database will be individual candidates, and these have to be separated because you cannot publish all the data on every time. Like some of them are private data for a few years. And for example, for M92, I cannot publish the different stars member of the stream because they are public. They are not public. So these kind of things have also to be taken into account. So I was mentioning that maybe we can do that with publishing individual stars on Vizier, which already exists and is there for that. And maybe putting the streams catalog, maybe with the CDS platform also, things like that, because there is this virtual observatories database, so which is kind of internationally based. We have to contribute that in that framework. Other thing was about the naming convention. Maybe we just need something like NGC catalogs, where we just say S and a number, S1 Sagittarius, S2 PAL5, S3 GD1, and so on. And finally was about the mocks of the streams. And the question was what kind of tools we need to transform simulation in fake observation to be able to really compare apple to apples. And I think it's something that we have to think in the future as well, to develop it more.
That's great, Guillaume. Thanks. I don't know if anyone wants to follow up on this. If not, we have Orlin next.
Yeah, I just wanted to summarize for my breakout room as well. Now it's still fresh, and I have some points that agree with the previous groups. In the last few minutes, we talked about the combinations of databases that we'd like, and we'd like to add footprints of surveys to those lists as well, if at all possible. But if anyone from the group wants to join in after I've did my talk, then please do. And on how to combine different projects that we're doing now. So the models that we have and the potentials that we use, we think it's very important to make some kind of standard here, but it's wise to find the most balanced way of doing this, because for some goals you need different kinds of potentials than for other goals. So we need to find like a general way to be able to combine this so everyone can compare apples to apples, as just said. Yeah, and then the different things that weren't brought up yet that we talked about is something that how we should go about implementing some effects in our codes that we see today, like the wake of the LMC or recoil due to the SMC. But the problem with this that was then raised by Heidi was that time-dependent analytical potentials are already quite difficult in n-body simulations. So we should do more research into this. And then we talked about what we want and what we will be able to measure from our mock catalogs of streams. And the main point raised here is that we need to make sure to know the limits of our simulations. So we won't do assumptions based on our models without putting it into the right context. And maybe it would be good to ask for advice in the cosmological community about how to go about these simulations, or maybe use one of their codes as a base for simulating our mock streams, so we don't have to go about building our own to only inject streams in. And I think that was it mainly.
Great, thanks, Orlin. I don't know if anyone has a follow-up on the points that Orlin summarized. Okay, Roman.
Right.
Go ahead.
I do too, actually.
Oh,
okay. Anna, you were raising your hand first, so go.
Yeah, exactly.
Yeah, it's a point that I thought was most unique from Breakout Room 4, and it ties on to what Orlin was saying about how can we make accurately account for the LMC. And so I guess we were thinking of kind of how can we move past the current basic approach where we have LMC as a analytic potential, so that it was, seems to be working well in this first order, but it looks like there may be other higher order effects. And one of the ideas that we discussed is producing sort of as an emulator where a grid of embodied simulations is run, and so that have like different LMC masses and different orbits and different like Milky Way masses, and then sort of then you we can interpolate between different sort of nodes in that grid to kind of fit the Milky Way and use streams there. And I guess as sort of one limitation, or it's kind of unclear how many simulations you would need to run to actually get the LMC to its kind of present day like conditions. How do you generate initial conditions? And then an idea was floated around that maybe the genetic modifications work that Andrew Ponson has been pioneering could maybe help with that are sort of kind of perturbing the initial conditions of like the model that kind of works well. And so that's what I wanted to bring up, because it's unclear if kind of how well this will work, and it needs some testing, and felt like maybe people would be interested in following up on that thread.
Thanks, Anna. So Robin, Nico was ahead of you, but I don't know if you were going to follow up on this or on Arlene.
I was going to follow up on what Orlin was saying, but I suspect that Nico might also be. So if that's true, Nico, you should talk.
You can go first. Yeah.
Okay. I just wanted to give a little perspective on things that we can do in cosmological simulations that I'm probably going to, or I'm thinking about releasing for public consumption in the next year or two. So right now, as we discussed in detail at several points in this conference, it's not yet clear how we're going to simultaneously model streams from satellites and globular clusters in cosmological simulations, which is really like the holy grail that I hear people talking about. However, what we can do right now is to produce synthetic surveys like the ones that I've done with FIRE and the ones that other people have done, say with Auriga or whatever. And these are sort of a little different than what's in the GUMS that Gaia produced, which is more tailored exactly to the Milky Way and has no substructure in it. It's a realization of the Besançon model. It also has no LMC, as far as I understand. So I wanted to say that in the next year or so, my goal is to adapt the code that we use to generate the mock Gaia surveys so that other people can run it on other simulations if they would like, and upgrade it to DR3 and release a set of mock data with DR3 error models. We've also folded in cross matches to Apogee into our error modeling and for the abundances that we track in simulations. And that is forthcoming shortly as soon as the paper gets through double collaboration review. Along the lines of what people were saying about a framework for time-dependent codes, Nico and others, and now my group, are all starting to look at this basis function expansion thing. Eugene and Dennis just had and Jason just had a paper on this too. The usefulness that I can offer there is that we can emulate the simulated systems by fitting these basis function expansions as a function of snapshot for a set of cosmological simulations, and give people sort of interpolated potentials to work with to see how that affects the assumptions in their models. And so if that's a useful thing, then we can also publish those. So I'll stop there, but if you have other ideas of things that you could use from cosmological simulations that are more simplified representations than the 10 gigabyte snapshots that we generally produce, then I'd love to hear about it from you guys, because contemplating now what sort of things should be involved in our sort of next public release from the collaboration. And so what would be useful to people in this field, including, you know, including a couple of galaxies that have LMC-like companions of various types. I'd love to hear other ideas about that here or offline.
Great, thanks, Robin. Nico? Just to remind everyone that we have a few minutes left before the coffee break.
Yeah, I wanted to summarize my room. So if Adrian have a direct opinion, okay.
Nope, go.
So in my room, we talk about how amazing Gulfstreams is, and Cecilia was in our room and gave us a very nice teaser of what's coming, which is radar velocities, proper motions, and metallicities. So that's amazing. We also talk about that from the observers, we'll need more catalogs from cosmological simulations to know where the streams are, or to have particle IDs tags. And then Ethan was also in our room and tell us that his cosmological simulations are dark matter only, but they're going to release initial conditions and everything, so people can resimulate them with different hydro routines. So that's super useful. And then we talk about that it would be nice to have like a database or a wiki with all the simulations that have been run for the Milky Way, if they have more catalogs, like very basic properties that each team can upload the information, so it's accessible for everyone in the community. And then we go on to say, okay, it would be nice to have all the information about what the streams that we have, observations, also simulations. So we said that we are a small community, we should be able to handle something like this. Maybe we can learn something from other communities from cosmology or planets that have a lot of data and how they keep track of all of what is going on. But we also discovered that need money and funding. And finally, we also talk about how to keep this conversation, because we really like conversations on Slack and overall. So it would be nice to keep this conversation. And someone mentioned that it's like a Slack software that is open source, so we don't have to pay to keep the conversations. And yeah, I think that was it. If anyone wants to add something, please.
You're muted.
Yeah.
Thanks. Thanks, Nico. So next up was Ting, and then Adrian.
Okay, so I want to bring up some points that our group bring up, but I don't think it's covered. So we kind of started from a different angle in terms of like what when we have all these data, simulation and models, what we think we are lack of. And I think a point brought up is like, for example, in those kind of like the S5 survey, I think what we lack of, we have data, but lack of is like people doing modeling. We have like only limited personnel doing that kind of thing. Because when those kind of spectroscope survey was started, we mostly focusing on getting observers, getting the observing running, and getting the data reduced and the produced catalog. But we didn't think further about modeling part or simulation part. And that's kind of the personnel we are lack of. And this kind of give to the future all other surveys, like especially the spectroscope survey, when they are kind of at this preparation stage, how much they think about this, about non-observation component in the spectroscope survey. And I think it's very important to think early and make sure to have voice from them. For example, like there are fire simulation and they talk about the fire collaboration or whatever. They have like things talk within their collaboration, but we want to make sure these kind of simulation people have voice in these spectroscopy survey and actively working together. I don't think there's much of like this in the spectroscopy survey. On the other hand, Alex mentioned that for all the photometry survey like LSST and all of those has all these simulators in to do data challenge or to help understand it. And another good example is once like the DES dwarf galaxy was all discovered, there are a lot of people doing simulations like Ethan Nadler get involved into the work to finally produce this kind of satellite luminosity function study. So I think the thing we lack of is getting the people from the theory side and from the observation side to talk to each other, and maybe make sure to have a platform to make that happen, to make all the studies more efficient. And related to this, at the end, we talk about like a GC stream study and what is lack of. And I think the thing is definitely there are more things we need to do in the modeling, but the modelers also would like to get more information about the chemistry and also like the tidal tails around the GCs from the observations more, etc. So I think we need something to make sure that there are communications between 3 different kind of subfield and to make more interesting science coming out. I hope I summarize. Yeah, that's all.
Thanks. So Rafael, you had your hand up for a while, so if we can have that, your comment very quickly, so we can move to
Thanks
a
a lot. I just wanted to add 2 points from group 7, which are, we talked about observational errors needing to be reported in a clear fashion and idealized in a standardized way, so that in the databases we can include, for example, the posterior distributions for velocity dispersions, or even fitted surface brightness profiles more easily in our own statistical model. And another point which we didn't, I think, bring up so far in the discussions is that it's not so bad if single scientists have their own specialized tools, because this gives us independent tests on the same question, and thereby, well, double checks. Yeah.
Great, thanks, Rafael. So sorry if you had more comments that we don't have to go, that we don't have time to go over, but perhaps you can continue discussions during the coffee break. So we're going to break now.
So I kind of took a script that I use a lot and just really pared it down to maybe highlight a couple things that are really unique to AMUSE. So like their units, their channels, and the bridge, which are, I think, are very unique, and you need to kind of know the AMUSE language for that. But then after that, I didn't have any firm plans. I don't know. I think each of us sounds like we had experience doing an LMC, including an LMC model or including subhalos. Maybe we could each talk about our unique experiences doing that. So I could maybe do the quick walkthrough of the basics of an AMUSE star cluster simulation, and then maybe you guys can talk about how you've used it in a bit more detail.
Yeah, that's good. I think Teresa said that you might not be able to do much, but could give it a try.
Sounds good.
Okay. Right. I think we need a bit of introduction to before we go to the details, right?
Yeah. I'll talk about. There's a few very unique things that are AMUSE only.
Yes, it is 10:30 now, so I think we should get started.
Let's go.
Yes, go ahead. Thanks.
Can I just take the share screen then, I guess?
Can you share screen?
I think I can. Yeah, there we go.
Okay, great. Yes, we see it. You're.
Oh, I see the wrong thing though. What? Nope. That looks wrong. Share screen. Share this one. Desktop one. Notice. Just everybody see the wrong screen. Because I have too many desktops. It's too. It's tough.
Well, it does say AMUSE demo, so.
Oh, it does?
Yeah, it does.
Oh, so what I
it was, yeah, it was, you know.
Okay, all right. So you see
the IPython, yes.
Yeah.
Oh, I see what's happening. So never mind. My other screen is disappearing while I'm sharing. Doesn't matter. Okay. So I'll do the basics here. Maybe I'll share my video if anyone needs to see my face. I don't know. Cool. So yeah, Python or AMUSE is basically just a super fancy and very detailed Python package. So you can write everything in a Python script, or in this case, like a Python notebook. It just has a bit of its own like unique language, which is the learning curve. But once you kind of learn its language, it is very helpful and very straightforward. So I'll maybe just like walk you through like a very simple star cluster simulation. So things I don't need to go over. So yeah, AMUSE has a bunch of ways of like setting up your initial distribution. So AMUSE calls like they're like an array or data set of particles, like these particle sets, but it's pretty much just a Python class. And so it'd have like, you know, stars.x is all the x coordinates, stars.y are all the y coordinates. So that I would just leave just looking through the documentation and the literature to how to set up your own initial distribution. Or you can, if you have your own favorite code, there's plenty out there for setting up your initial conditions, and then you can just read them right into an AMUSE particle set as an array. But so one of the fun things about AMUSE is their unique use of units. So instead of like just a times like you would use for AstroPi, they have this like horizontal bar, or sorry, vertical bar to denote their units. So that's unique to AMUSE, and it doesn't always play well with other things. So I think AMUSE has like, if you want to like take this value and use it with AstroPi or something, or GalPi or something, you always have to do like a or cluster dot like value in or something, and then it drops the AMUSE units and just gives you the value. But if you're using AMUSE, you need to kind of keep track of their funky use of units. And then you also need this converter. So the way to picture AMUSE is that AMUSE is kind of like, or your script is like the trunk of a tree, and then all the potential other codes that you want to use are branches. And so you're constantly having to send information from the trunk of the tree to the branches. Or so you're sending information from your script to all the other codes. So once you set up your initial conditions, you need to keep track of this converter variable, which would tell a code how to switch back and forth from n-body units to SI units or something like that. And you'll see why to do that in a second. So here I've just set up, I now have this like Python class essentially called stars, and it has all the masses, positions, and velocities of my initial stars. And this last step, I'm just scaling the initial conditions because I'm going to be using softening in my code. So the initial conditions assume no softening. So if you're going to have softening and you want it to be virialized at the beginning, then you have to do that. So then if you want to introduce like an external galaxy, which I've called here as a galaxy code, this is the very quick and easy way of just taking a GalPi potential. So in this case, Joe's midway potential 2014, and it's one line and it turns it into an AMUSE code. And so every time galaxy code is called, it calculates the galactic force on all the stars in your star cluster. So to explain these other parts, I kind of have a slightly more complicated demo. So just, if you know AMUSE, this isn't too, if you know GalPi, this isn't too crazy. But essentially what I'm doing here is just defining a potential for the LMC, putting it around Milky Way 2014, and then combining those two potentials. And then again, I use this toAMUSE call from GalPi to make that potential. So here I have to, so whenever I run my AMUSE codes, I always just let time start at 0 and go forward. But my GalPi potential might not want to start at 0. I might want to start like the location of the LMC 1 gigayear ago or something like that. So that's why I have this telling the GalPi potential where to start. But that's nitty gritty stuff. I just figured someone might ask. And you can also choose whether you want your potential to evolve forwards or backwards in time, depending on what you're doing. So that's a quick way of doing a time-dependent potential, but let's just stick with calling a static potential for now. I just set up an orbit and move all the star cluster stars to that position and velocity in the galaxy. And then here we got to make one of these branches now. Okay, so we have this stars data set. One branch would be the galaxy code that we made using a GalPi potential. But then here we need to tell how gravity is going to work for the stars in the cluster. So for this particular example, I've used a BH tree, the Barnes-Hut tree, I think. But that's just one of many n-body codes within AMUSE. And so the beauty of AMUSE is that if I want to change this, I can really just type in one of the other ones they have. There's PH4, Gadget, anything like that. And it's just like one line replacement. And you can choose which n-body code you're using. So it's kind of nice. But again, you have to give it that converter variable I mentioned above. That branch needs to know how to switch back and forth between SI units and n-body units because bh-tree uses n-body units. Can be very parallelized very easily. Just give it number of workers. If you have 4 CPUs available, throw in 4 there. bh-tree doesn't use GPUs, but other codes in AMUSE do. So you can have GPU workers as well. And then this is how you set all the parameters for that code. So again, you have to look in each individual code's documentation on the AMUSE site or in the code itself. But you know, you can set softening length. This is a tree code, so you need the opening angle and the time steps. And then you have to send the star particles into that branch of your tree. You need to give bh-tree those stars. But even though I've done this, so I've given bh-tree my stars, there's effectively 2 different ways. There's 2 different star data sets now. There's the local one here in my Python script, and now there's one that only bh-tree has. So getting to one of the weirder parts of AMUSE are these channels. You have to set up these channels to allow the trunk of your tree and the branches of your tree to communicate. You need to be able to tell it, so channel from stars to cluster code. I'm sometimes going to be sending things from my local stars dataset to the stars dataset that's in cluster code. And vice versa, I need to set up a channel saying I'm sometimes going to want to bring the information for the stars that's in bh-tree in my cluster code back to my local script. So this is between the units and this channel thing. Those are 2 of the weirder parts of AMUSE.
Jeremy, can you take a question?
Yeah, absolutely.
David, go ahead.
Oh, sorry, I didn't see the hand up. Yeah.
No worries.
No worries. Yeah, so does one have to install all these n-body codes separately, or they come together with AMUSE when you install AMUSE?
Yes or no, your choice. You can do the base install of AMUSE, which I think they call like you pip install the AMUSE framework, and then you would install the n-body code separately. But there is a big bulk install where everything comes with it. I think everything except for Galaxia is a thing that AMUSE can use, but doesn't come with it. You have to install that separately.
I see.
Everything manages to compile every time, so beware that it's a very heterogeneous framework, and it's actually a huge effort for maintaining all these codes. Be prepared that some of them might not work on your specific installation, but many of them will still.
Yeah, absolutely. Good point. You got to keep track of your configuring and compiling and installing to get everything to work correctly.
Thanks.
Cool. Yeah, no problem. And then, so for this example, I've also added, so let's say I want stellar evolution. This is yet another branch on my tree. So now I have 3 branches, right? I have the gravity between the stars, which is cluster code, which is bh-tree. I have my galaxy code, which is a galpi potential. And now a 3rd branch is stellar evolution. So I add my particles to that, and I just have to set up new channels, right? Sometimes I'm going to want to send masses from my local data set to the stellar evolution code, and sometimes I'm going to want to pull masses from the stellar evolution code to my star data set. So yeah, units and channels are the weird part, but then you'll kind of see why when I talk about bridge, which for me personally, the bridge is like the most powerful part of AMUSE, because this is what brings these codes together. It bridges them, I guess. So you initialize your bridge, and then you just start adding systems. So this one, gravity, so I name my bridge gravity. I add system, cluster code, galaxy code. This tells you that when you're calculating the forces between stars in my cluster code in bh-tree, I also want to factor in forces from galaxy code. And so you get now you have an external tidal field. So that could have been a static Milky Way potential, or that could have been the time-dependent one I made. If your galaxy code is time-dependent, then you have to add it as a system that depends on itself. It needs to know to update the time within that potential. But if it's a static one, you don't need to. So maybe to show a bit more how even more useful this is, let's say let's assume I had an array of subhalos. And I don't want them to I don't want subhalos to care about each other's gravity. So AMUSE has this drift without gravity code where nothing happens. But if I have this subhalo code now, which is just the locations of a bunch of subhalos, I would make a different bridge where I would say stars in the cluster now depend on my galaxy code, my background potential, and depends on the subhalos. So it's really just one extra line to say, let's add some substructure to this galaxy model. Another extra line that says, oh, the subhalos care about the background galaxy, so they'll still move around and orbit within the galaxy, and they'd be modeled separately. But again, let's go back to the simpler example. And then it's just a while. Pardon?
Adrian, I think, had a question.
Yep,
well, it's a more technical question, so I maybe you should keep going and maybe I can ask it in a minute.
Yeah, I'm almost done. So yeah, sounds good. And then like the actual evolution part, now that I've set up all the branches of my tree and the tree trunk and stuff, then you can just write your own while loop and decide what you want to get out as the simulation goes. So I kind of set how often I jump in time. I set this DT parameter. And in this quick example, I just ran it 1 million years. So the way AMUSE, the way they suggest to do stellar evolution in the book, and I think this is what Embody 6 does too. You call your you evolve your stellar evolution code half a time step. Then you call the channel and say, hey, I want all those masses back from the stellar evolution code. I want to send those new masses to the cluster code. So you're updating all the masses in the code that's evolving your stars. Then do the gravity evolve in your bridge. So this is evolving. You get all new positions and velocities for your stars. Copy all those back, and then do the stellar in 2 halves. And do whatever you want. You can output the time step. You can plot it if you want. You can remove stars. If you want to remove anything that's like 10 tidal radii away from the cluster, you can just cut them or something like that. So you can manipulate them because you've brought them all back to the channel. What I haven't done here is send anything back. So if you do manipulation, you need to send them back to the respective codes. And then bring everything back when you're done, and it's just like Python. You can make little matplot libplots and stuff like that. So the biggest things to wrap your head around are units, channels, and the bridge. That's kind of the unique AMUSE language, but after that, a lot of it is just Python.
Awesome. Thank you so much, Jeremy. Any questions for?
Yeah, I can repeat stuff too. Sorry if that was too fast. I was just kind of plowing through.
Martin?
Hi, I wanted to know in which language is done the integration and the computation of the stellar evolution.
So that's unique to every code. So I wonder if I have. So pretty much what people do, or what the AMUSE people do, is that they would take an SSE code that someone has written, and then they just write a little like wrapper around it. I think in Python. If I could show you really quick, I will. But if I can't, I don't think I can real quick. Unit test support. Oh, community. Yeah, they take a community code like SSE. Right. So every community code that's written in whatever language that code is has one of these interface.py scripts. And so whatever the things that AMUSE needs to call, like this initialize evolve star, they have figured out how to send that to the actual code and how it's been written in its native language. So whatever SSE was written in, that's how it'll be done. Python is just used as an intermediary between the two codes. So bridge, I guess, is the thing that's purely AMUSE, and I think that's Python.
Yep.
Yeah.
I think the philosophy is indeed to keep the codes as intact as possible, just adding these interfaces which perform some standardized operations like advance particle for a given amount of time, or change the masses of particles, or compute the gravity at a given point. That's exactly how this bridge works in this case, that the AMUSE framework tells the gravity solver, in this case, whatever is BH3, that there is another external source of potential, and at each time step of the internal evolution. No, so I'm wrong here. It's done at the bridge level, right? It's done at the bridge level that these two codes talk to each other, but that's right. This coupling is operated at the level of AMUSE, but all the details are specific to each code. So, for example, when you're doing the n-body integration, the stellar evolution could be just replaced with some other code, and the n-body wouldn't notice anything, right?
Yeah. Yeah, so you could essentially add, and I think they give examples on their website, you could add your own stellar evolution code really easily. It's just a Python class that has to have like these 4 key functions, like Eugene was saying, update mass, something like that, or evolve mass, and you can put in whatever you want for how the mass evolves. So same thing if you want to add your own potential, like we did with GalPy, there's just a potential shell that has 4 or 5 key functions that AMUSE needs to be able to call. And then it calls GalPy in whatever language GalPy is using for that potential.
Thanks.
Rodrigo?
Yeah, so thank you very much, Jeremy. I just wanted to know whether this demo will be available for us to play with.
Oh.
It's part of the community effort, right? Isn't it?
Yeah, I can put it up. I don't know, Anna or Adrian can maybe tell me a place. I can give it to one of you and you can put it up. I don't think it requires anything magical. Yeah, I can put it up.
Really fun to play with. Thanks.
Yeah, if you want to play with it, yeah, I'll put it somewhere that Anna or Adrian tells me to put it.
One option is if you have a GitHub account, you could put it in a gist and share the link, or you could actually upload the notebook file to the Dropbox that we use for talks and everything. I could share that link with you, whichever is easier.
Send me the link. I have GitHub, but I've never gisted anything, so it'll be easier just to put it on Dropbox.
Awesome. Thank you so much. I think, Eugene, did you want to show something in the last?
Well, I guess you have to wrap up very quickly. But
yeah, we have to wrap up quickly. But I feel like since anyway,
okay,
you should go ahead.
I can show you real quick. I essentially prepared the same example, but of course, we're using my own native tools. Instead of GalPy potential, I was using the potential from Macmillan 17 implemented in Agama. But the idea is the same. You set up your n-body code, the King model in this case, and set up a bridge and run it. What I do have is I wanted to show how it works actually, and hopefully it will work.
Wow.
Okay, let me.
Like we've done it all, running code.
Running code, yeah, I don't see.
Yeah.
That's where it is. Okay, so it's a star cluster orbiting in a galaxy. You don't see the galaxy, but imagine that it's somewhere. And the star cluster is evolving using this direct summation code, some sort of Hermit solver. And the galaxy provides the external potential. So you will see that the cluster starts to lose stars as it approaches the tidal radius. Yeah, so I think this is the kind of thing that you could do also in various other frameworks. I guess AMUSE adds the possibility of two most important things. One is to switch between the implementations fairly easily, as Jeremy said. In the ideal case, it's just replacing a single line of the script with the name of a different code. And the other is that it allows you to couple different codes from different physical domains. So in principle, you could, if you like, you could do this stellar evolution at the same time. You could also add hydrodynamics, and there is even radiative transfer, which people doing the evolution of embedded star clusters are all happy about. And in terms of performance, it's almost native, I believe. So native to each code. So if you're running a huge n-body simulation over a huge cluster, it actually could be done all in AMUSE, I believe. And they had an example of doing it like in a grid network over several continents. So yeah, I think it's a very useful tool, and I haven't used it myself actually for doing this analysis, but yes, several of us have done it. So maybe you should keep this thread where people can come and ask for further details and suggestions.
Yeah, thank you so much for fielding the questions today. And I'm sure like the question will come up of you sharing this script. It's really awesome. Let's just say like seeing
Absolutely.
the live evolving. So it'll be great. Okay, I do want to like to leave you all with 4 minutes of a break at least. But yeah, let's continue the discussion on the Slack thread there on the Day 5 channel. And thank you so much, Jeremy, Jean, and Teresa for both like work today and all of the future questions that are coming up.
So I suppose continuing on then from some of the points that were raised earlier, I think the things we want to think about are the kind of modeling tools that people want. And I suppose that relates to your point that you just raised, Eugene, in the main room, the kind of, or even sort of demonstrations or kind of community shared sort of tutorials that people that are sort of lacking maybe. Also about some kind of maybe homogenizing the current tools that we have. Something on sharing results and the various discussions about basis function expansions, and then sort of standardized testing of different modeling approaches. So I don't know whether anyone wants to kick off on any of those points.
I could bring a point that we had in our small discussion meeting, that is there a distinction between models and simulations that we need to keep in mind? Like models of a stream versus perhaps a simulation that provides a stream. I would say the model perhaps is something that you tune to reproduce the properties of a particular stream, whereas a simulation is more like something that generates a stream and then you can use that as a mock data, for example, but maybe I'm wrong.
Guillaume, did you want to say something to that?
Yeah, I think also it's a good, I completely agree with this question. And I think that one of the differences as well is between real simulation as a collisional or collisionless and spring particle, for example, which is more for modeling the orbits, and you cannot resolve everything from that. Yeah, when simulations can be, from my point of view, is more n-body simulation really, but it's not really a model for that. You know?
No worries, there wasn't really a question, Adrian. Just a terminological thing.
I see. I would also expand modeling a little bit to include inference and statistical applications to data. And there you might not want to put an n-body simulation, like you might want to use n-body simulations and cosmological simulations to motivate a method that approximates things enough that you can use it very quickly in inference problems. So to me, there's a little bit, it's a gray area, but there is a little bit of a distinction.
Right, so which of these things we want to homogenize in the first place? I believe that part of the community is indeed the point is that everyone is using their preferred methods for modeling the streams. And that's, of course, we would like to have perhaps results from different methods applied to the same stream in some sort of controlled setting. That was partially the purpose of Gaia Challenge, I believe. But maybe we should also aim at some sort of concerted effort to model a particular well-studied stream with a variety of methods, and in hope of finding some strengths and weaknesses in application to real data. I guess in some fields people do that, and in cosmology, also in the modeling of galactic nuclei, there is another effort that is undergoing, applying different modeling tools to measure the black hole masses. And I guess something similar could be envisaged for streams. What do you think, guys?
So using actual data, is that the proposal? Yeah.
Both, yeah.
Okay.
Yes, but both the mock data and applying it to real data with their pitfalls and so on.
And on the real data, the test is whether everyone recovers the same answer.
Mm-hmm. Yes, well, are they uncertainties compatible?
Right. I suppose that's the thing, yeah, sort of knowing ground truths, isn't it? And what numbers you're trying to recover from. I think one of the issues with the Gaia challenge was agreeing on what people were trying to constrain from their methods and what they then reported and what was being compared. So the challenges were related to sort of large scale potential constraints and from streams, and then, you know, it's is it comparing acceleration at the mean distance of the stream or some other quantity? Yeah, Monica, would you like to say something?
Yeah, I just wanted to add to Eugene's comment about you know, the need for being able to compare different methods. Sometimes unless you compare different codes or different methods, it's not easy to tell when your errors on whatever parameter you're estimating comes from the data or whether it comes from the method. And methods actually do, you know, sort of have either systematic or random errors that they introduce. And I think that's really valuable to have multiple different methods on the market which one can compare.
This is slightly orthogonal, but related. There's also Jason raised some points earlier, and there's some discussion in at least the breakout room that I was in earlier about different sort of software packages and tools for generating parts of the models that you then use to compare to data, and whether it's useful to coordinate better or to have separate packages, and that's okay. And I don't have a strong opinion there, but I do think that at some level we could standardize some of the sort of tool level things like implementations of potentials, integrators, things like that, while still having some of the method, the like direct applications to data and sort of the next layer built on top of that be separate, so that we're using a shared infrastructure underneath, but we do have some reproducibility. Like, I don't think we need to all implement like 8th order Runge-Kutta integrators for reproducible science. I don't think that's a useful use of our time, but we should all be trying to model streams using different methods and inference, you know, different models at the statistical level. I don't know how people feel about that, but.
Yeah, Dennis, would you like to? I should also say, would somebody like to take some notes? That would be great.
Taking notes, yes.
Physical or
physical file will come later.
Thanks, Eugene.
I guess I was going to say that, I mean, I think there's also a slight difference between, like, you know, what's happening at the state-of-the-art level with like fitting versus what tools the community can use to like do things they're interested in, right? Like if you care about perhaps like satellite orbits, you may not care about really precise things that we're currently looking at with exactly how things are deforming. So I think at leading order, just having, you know, having, let's say, GalPy or Gala, having the option to add a rigid LMC in, which falls in and kind of you account for the acceleration of the Milky Way. That's a good, like, you know, first order approach that will give you most of the right answer and it can be easily implemented and it's still really fast, versus taking, let's say, like the basis function expansion result from Nico or from Mike and trying to inject that into one of the code. It's still possible, but those tools are currently state-of-the-art tools that we haven't even explored yet. At least, like, Sophia is currently using those tools to look at whether or not the streams are even sensitive to those deformations. But I feel like people are currently using, you know, GalPy, right? Just the standard Milky Potential 2014. And I think the kind of analog of that would just be adding in a rigid LMC that moves and the Milky Way moves. And that will get things roughly right.
Yeah,
and
I guess
go ahead, Eugene.
As you mentioned the other day or the other time, that it's actually very easy, and you can do it essentially in a few lines of code, right? Integrating the orbits of the LMC plus Milky Way in the given potential, and then plugging it into your stream model so that you have a time-dependent potential out of the box.
Yeah, exactly. So it can be done in an easy way that's easy for most codes. Yeah, so I feel like that's probably enough for most applications. Obviously, if the thing you're interested in is do the deformations affect the streams, then of course you need it, and that's something that still hasn't even been published yet. So those are kind of very cutting edge questions, I think. But so I think it can also be a combination of tools, right? For something where you want to do it very quickly and want something very rapid, you could just have a rigid LMC. And if you want to explore these really fine details, then yeah, hopefully, Nico and Mike will release these basis function expansions so people can then test that particular aspect of it.
Yes, Mike, do you want to comment?
Yeah, I'm not convinced that we know enough about the LMC to make a fiducial potential yet. Like I think it could do more harm than good, because if we generate something that's a fiducial LMC and everyone just uses it and we start accepting it as the potential, like Milky Way 2014, then we might just be hurting ourselves going forward.
Well, for the case of Milky Way, we have several choices. We have at least Macmillan and Bobby's potentials, which kind of straddle more or less all the other realistic cases in between. So it's a good idea always to explore at least those two. And I think the same is probably true for Milky Way plus LMC interaction, that you don't want just a single model, but you would like to have a range of models to play with. That's why it is more about the method rather than providing just a single choice of potential.
Sorry, I don't follow the last statement that you made about
providing the method for quickly generating the Milky Way plus LMC potential, in which orbit each other. As you change the parameters of the Milky Way and LMC, those would be regenerated on the fly, right? It's like fraction of a second, because you are doing a two-body interaction essentially.
Sure.
So you're saying sorry to jump in and rephrase, but you're saying use this at like the idea of having a standard model. Maybe that's not the actual deliverable. The deliverable is the infrastructure to be able to put in different parameters and then we can standardize the Milky Way plus LMC.
Exactly. Model. In a way that people can take the Bobby's potential and change the mass of the halo and explore how it affects the result. In the same way, you should do it for the Milky Way plus LMC system.
I think Guillaume had his hand up first.
It was also to know if there was a possibility to put also different type of dark matter in this kind of models, to have a standard way on also these mean field theories, like MOND, for example, is a mean field theory at some level. So is there a way to do that? And is there any interest to do that as well?
I would say it's a very valuable thing. It's underexplored precisely because there has been no real effort in putting it into easy-to-use tools. Anyone with a background in MOND, if they can jump in and say whether it could be used in the same way as we do it for standard potentials. Guillaume, you probably have the most experience with this.
And I would even generalize and just say that it's not just MOND. I mean, there's also other dark matter theories. So I think it's just that so much has gone into Lambda CDM. We need equivalent efforts in these other models if we want to be able to easily swap them out.
Yeah, that was my point. Sorry. Yeah, we're just meaning about MOND because maybe it's kind of more difficult to implement than warm dark matter or SIBM. But yeah.
Can I just briefly jump in on that?
Yeah, go ahead.
I was just going to point, I think part of the problem with these other models is that the Poisson equation becomes nonlinear, and so it becomes very difficult to build models. The nice thing about standard gravity is that we can build a model for a disk, we can build one for the halo, and we can just add them all up. And once you're talking about things like MOND, self-interacting dark matter, you have to fully solve the Poisson equation every time. So it's just it's doable, but it's a lot harder. So again, yeah, I think I want to kind of echo Eugene's point that like really like better tools, like people like deliverables would be like tools to compute these things would be useful.
Yeah, well, people certainly can do it even in live antibody simulations. Maybe Phantom of Ramses is the approach that integrates at least one possible alternative gravity model into a conventional antibody code.
Yeah, exactly. Yeah. But the thing is, you have to go by grid at some point to compute that, because in that paradigm, MOND is a kind of a mean field theory, where every time you have these dark matters that evolve with the bionic matter, and you have nonlinear effects that really hard to take into account.
Dennis, would you like to say something?
I guess just in terms of like the idea that it's, like what it means to have like a standard LMC model, like kind of like what Mike and Eugene were talking about a little while ago. I mean, like what we're finding when we're fitting the streams, like in Nora's work or in kind of my fits to Orphan/Chenab, is that like a single model that we have with a LMC of about 1.5 times 10^11 can fit most streams relatively well. And that single model, plus even like the Galpai potential, the Looking Potential 2014, plus that LMC does pretty well for all streams. There is some subtlety going on with like the response of the stellar halo, that kind of the direction that the stellar halo is pulled in perhaps doesn't exactly match, but we need to do some more work to understand, like, yeah, I mean, I can talk to Mike about, there's some precise details about that is still being worked out, but overall that wouldn't be like a bad starting point, but you have to understand the limitations to anything, right? So if you find something really weird in that potential, then you should be very careful in trusting that. But if it broadly agrees, probably it's a decent starting point. And then if you want really precise things, you may need to vary those parameters and find the optimal ones. But yeah, I think it wouldn't be a bad starting point, at least.
Sorry, Nathaniel, just to respond to that point, and I think it connects to what Mike was saying before, that maybe it's too early to standardize Milky Way plus LMC model. I would say the same thing about the Milky Way model that everybody's using, but there is still some utility in it, I think, in that, like, at least this is now even if we have a bad Milky Way plus LMC model, it is a comparison point to the static Milky Way model. And maybe if we're very clear about saying, like, only use this to assess like whether you think the LMC could be important, and then you have to do something much better if you actually want to model this stuff, that might still be useful. Nathaniel?
Yeah, so I want to agree with that and build off that. Right, standardizing the potentials in this way is just sort of choosing a single best fit. I think one of the things that would be most useful to accompany the architecture would a likelihood surface or something, so that you don't just choose your single best point when you're iterating over this, but you can just directly sample from some likelihood function to generate your masses or whatever other parameters are involved in the model.
We should ping, I guess we should ping Paul Macmillan for his MCMC chains. It wasn't made public yet, right?
It is if you ask him, but it's not like on the website or anything like that.
Those only span a limited range of what's possible for Milky Way potentials. I mean, there's tons of stuff that's missing from this. Like, we shouldn't fall into this trap that, like, because we have MCMC chains of this one model, this one family of models, that we've solved it, like that we're good to go now.
Well, it's certainly better than none, right? Or better than one. And
I don't know, is it? I mean, are we sure?
It is. No, it is sure is, because the way that you make a statement about, let's say, what's the behavior of your favorite global cluster in a potential, if you just take one potential, you might be misled, right? If in 99 other cases it behaves completely differently. So it gives you some flexibility already to explore. It might not give you the ultimate result, but it is better than just a single answer.
Slightly agree with Mike, but I agree with all of you. But I think the point is that the MCMC samples will give you a sense of the precision, but that's not capturing the spread in systematic issues with the global model of the potential. So don't fool yourself into thinking that just because you're using the samples from the MCMC chain that actually represents the true variance of the models.
Bayes is hard.
Sorry, go ahead, Mark.
I was just saying doing anything in a Bayesian way is hard. It's much easier to do a machine learning thing and say, we predict things, and then you're done.
I just wanted to kind of echo, yeah, I mean, Mike's point as well. I mean, obviously, like whenever you have something like even Macmillan's chains, right? I mean, he used, some of the data he used was in the inner part of the galaxy. Some of it's beyond 50 kiloparsecs. And that stuff in the outskirts is already being affected by the LMC. So like, even if the Milky Way happened to have the functional form that he was fitting with, there could be biases due to what's happening in the outskirts that wasn't accounted for. But I think everyone should understand that no matter what we do, there are caveats, and that you have to understand those caveats. So like, even if there was, let's say, the LMC was included in GalPy or in Gala as a flag you could turn on, and it could come with some fiducial mass that, for example, can reproduce the streams from like Nora's work or from Orphan. There's still that limitation, and that may not be right, and that everyone needs to understand that. I mean, we can also provide chains, but even those, may not capture the full picture, right? Because a lot of these things were only fit, like even like Eugene SAG models were only fitting the SAG data. They weren't fitting all kinds of other aspects of the Milky Way, although Eugene did use a nice Milky Way disk. But yeah.
Yeah, Mike, do you want to?
Yeah, I think that's a good point. I think now that we're saying things like everyone should understand where the models have limits, that's a place where we should figure out how to tell everyone where the limits of the models are. I mean, maybe that's like the thing. If we make a fiducial Milky Way and LMC, explain to people what the range of things you could use it for would be.
And there will still be people who come in and import the package, as Joe and I'm sure me and Eugene also know, use the potential and draw, misleading conclusions from orbits they compute in them. But that's okay. Like, that's going to happen no matter what we do. We just have to be good about communicating the limitations, I think, and it's up to them.
So yeah, I suppose I don't quite follow the argument. So I mean, isn't there value in something suitably flexible that we're well sampling sort of all possible model space somehow, and that's sort of encompassing all of our uncertainties? I understand we always want the kind of get out of like, yes, this might not work because of limitations, but don't we want to, I don't know, shouldn't this be a goal that we're trying to edge ever closer to really fully understanding and fully sampling?
Absolutely. Yeah, no, I think so. It's just that I think we were just trying to emphasize not to overinterpret what it means to have those samples. Dennis.
Yeah, I guess I wanted to, I mean, there's things happening that are state of the art, like things that have to do with very subtleties in the deformation, and like that perhaps shouldn't be part of the standard vanilla model everyone starts importing, right? Because we haven't fully understood what those things are doing, and we haven't even explored, the consequences. But at the same time, like people are using, Milky Potential 2014 as the standard potential, and it's fine to have some kind of standard. But yeah, I think if we don't release the LMC models, then many people will be missing out on those effects, right? So like, it has relatively large effects on certain dwarf orbits, for example, and can help people interpret certain things. If people want to understand really precise effects, they would need to put in better models, or perhaps collaborate with some of us that have those models that we're currently testing. And they'll eventually become public, like Mike and I were talking about Mike's models becoming public at some point, Nico's models, some of the simulations can become public. But something that will evolve over the next few years. But I think having something which roughly captures what we're seeing and is able to match data can be a starting point.
Yes, Joe.
Yeah, I think we just want like a hierarchy of models, I think, where some are simpler, it's just kind of standard disk halo bulge. Some are, and then you have the other end of the range where you include the whole time-dependent deformation of the halo due to the LMC. Maybe not something that people, some people in this room and the people at this workshop do this, but you have to remember that people are using these potentials to compute like actions for like millions of objects, doing MCMC or like doing Monte Carlo sampling, to get these things for large surveys. They're not really going to be affected by the deformation from the LMC if they're just looking at disk stars. And certainly it's going to be way too expensive to do anything reasonable with a deformed potential. So I think we just need to have like a hierarchy of like models of different complexity that are useful for different contexts. And so again, I think it's again just asking also for tools rather than just a single best fit potential.
So we have a couple of minutes left. Does anyone want to bring up anything sort of unrelated or, Dennis?
I guess the kind of point about, I think people have discussed it in one of the breakout rooms about having like a standardized way of describing the potential as well, like having a standardized basis function or a standardized, I don't know if we're quite there yet to pick a single style, right? So there's a few different things that are out there right now. There's kind of multipole expansions by, kind of Eugene Spline multipole expansions. Other groups also have multipole expansions. There's the basis function expansions. There's Mike's basis function expansions. And so I don't think we're ready to kind of pick a single standard yet, but I think if we do fits, let's say that you are able to fit something with the deforming model, then it would be nice, obviously, to release to the community a way to do something with that fit, like to kind of evolve something in that fit potential. I think no one is at the level right now of fitting any kind of deforming models, but once we do have those, then it should be released. And the same thing like with Eugene Sag fits. So like those were done with these very weird shapes for the Milky Way halo where it twists. And that was released. So you can download a gamma and then get that potential. So I think as long as it's accessible, the fact that they're all a bit different is okay. But I think we shouldn't, at this point, be picking a single standardized technique because there's many things that are being tried. We don't know which one is going to work in what context. So I guess I just want to say that we shouldn't pick a single standard for now.
Cool, thank you, Dennis. So yeah, I mean, I think we should just go back 20 or so seconds left. Thanks everyone for the nice discussion. And yeah, see you back in the main room.
Okay, so we have 15 minutes for this part so that we don't go over with the closing ceremony. So we can have like a very quick recap of the breakout rooms. I don't know if anyone wants to volunteer from either of the three rooms. Okay, so if not, then maybe we can start with room 1. There you go.
Okay, I'll talk for room 1 because I promised Cecilia if no one volunteers, I can take. A lot of things in room 1 for data related stuff. We start with Gauss stream, which I think is very, I think everyone should know that there will be a new update on Gauss stream soon, and there's a lot of new features, including like updated, more precise stream coordinates, like and stream polygons, and also like where this information coming from a particular paper. So definitely looking forward to that. And then we also talk about like in the future, like for example, Foremost is going to produce 300 million of spectra and catalog with 300 million targets. So what kind of like ways that people wanted to what's the best way for people to get those information from the public data release? So do you want to download the entire catalog or via some searching? And I think the answer is that we should have something like fit similar to Gaia and make sure that all of those things has Gaia ID. So it's much easier for us to cross match with Gaia proper motion. And then we discussed about creating the repository for either like confirm the spectroscope member or some targets for future stuff. So we get a lot of discussion that on our libraries and talking about how these future surveys will do all of those follow up. So we mentioned about foremost we'll do very simple target selection. So they might not cover everything. So they welcome everyone, other like surveys to observe those targets, while DESI will actually have high priority targets on R libraries and BHB, those rare stars. So hopefully we'll get a complete set of those rare tracers, I think within the magnitude range of DESI. And there's also discussion about if we observe our libraries only with one epoch, like what DESI probably will do, then we need to understand the template of the R library velocity variation better, so we can better calibrate them with only one epoch. Then the last point we talk about is how to make an online catalog. So Alex G brought up this AstroCat software that was used in the, I forgot, it's transient community, I believe. If I'm wrong, please correct me. But they use that and try to kind of collect all of those things. So we brought up a thing like we need to make sure, like if the data is not published yet, sorry, if the paper that's used to write those are not published yet, if it's internally released, then we need to make sure about the data release policy from those collaborations. But then at the end, I brought up the question is like, say if a collaboration published a paper making some plots, they didn't have a public data release, but they essentially plot all of those things like the I and DAC of all those information. So does that also consider as actually published data, and the community should have the right to get all of those information for what is presented in the paper. So that's kind of a gray kind of regime in terms of not a table in the paper, but is a plot in the paper that we can digitize. But it would be better if it's also essentially a public resource. So that's kind of the thing we all talked about.
Thanks, Ting. That summary was great. Does someone want to summarize from the modeling breakout?
Yeah, I can talk about what we spoke about or what was mentioned. So yeah, we started with some sort of points about the difference between modeling and simulation, and whether and how sort of modeling was like, I suppose, a fast way of trying to reproduce more detailed simulations, or modeling could also be to do with trying to construct some likelihood function. We also talked about the ways to standardize potential models, and I think there was some reluctance at the moment to completely to be too prescriptive about what the Milky Way plus LMC model should be, although it's I think it was accepted that a sort of bad version of this model still had utility. It was important to make sure that people were aware of the limitations of anything that was provided at this stage. It's all very kind of cutting edge stuff, and so I think people were sort of happy that there were several different implementations at the moment, and that potentially there wasn't need to completely standardize everything right at this moment. I think there's some desire to have sets of tools for computing or sort of running simulations or models in kind of other dark matter models or alternative gravity theories. And I think that was that's something that's lacking. But I mean, it's pointed out that these calculations are just quite difficult to do because of the non-linearity of Poisson's equation in many of these things, in these models. And then, yeah, I suppose as one of the points that was raised towards the end was the need for kind of hierarchy of models, that it's good to have a standard model that works well for the kind of the disk of the galaxy, or sort of nearby disk stars that people could quite happily use, and then ever more complicated models for the more time-dependent outer parts of the halo. Yeah, if anyone would like to say anything more about what we spoke about, then go ahead.
There you go, Eugene.
Yeah, just to stress that there was a kind of dichotomy between the desire to provide some sort of tool that is easy to use out of the box, and the desire to make people aware that this is not the only answer, and there is a lot more flexibility. And even if you provide, let's say, an MCMC collection of samples, that still does not represent the whole range of possibilities, so that people should be exploring things out of this box. I don't think there is a unique answer there.
So if if anyone wants to follow up on this, we have a little time, and if not, then we could have the summary for the last breakout room, which was the simulations one. I think Adrian was in that room, perhaps.
I was in modeling.
Jessica?
Ah.
Yeah, I can do it. I think I need to check the notes. But so we talked quite a bit about what kind of mocks people would like to see and what kind of mocks will be available. And so one of the interesting points, for example, being having access to merger trees, or knowing which stars were accreted from which mergers. And if I can group it all together in general for that, but also for predictions for other surveys and making mock catalogs for specific surveys. All simulators said, yes, we're very interested in these kind of things, and we're happy to work with you, and especially collaborations are very much encouraged, and we're very happy to do that. And we like to work with you, and we want to see what you do with our data, and we want to advise you and help you. But we also want to take care of our own students, and we want to make sure that we don't endanger any projects by students that are ongoing. And so please contact us and please work with us. We're low, I think in a way, on the simulation side, and especially on the mock catalog side, it's basically the same as is the case in preparing for future surveys. We're low on people power. So there are tons of projects that could be done, and there's tons of projects that people would love to do, but there's not enough people to do them. So I think for both groups, please get in touch. If you have a good idea, please get in touch with any of the simulators in this community. And I think those were the key points, but if anyone wants to discuss any of the more smaller points that we discussed, then please. Yes, Robin.
I'll just throw in there that
it's also fair to ask us what's coming down the pike, like what we're planning to do with simulation data in the future.
Absolutely.
Because most of the time, if something that you are interested in using is like about to be made public, we'll give you early access to it. It's okay. Like, this is not usually that cutthroat. So just check in with us too and see what we are planning on doing as well.
Thank you for adding.
So what are you planning to do?
So, like, for instance, right now, we're working on upgrading Gaia synthetic surveys for DR3 models. We're adding apogee uncertainties to the metallicities that we track in the simulations, and we're getting ready to release those. I had a side thread with some people that were like, what about RLIRE? Well, it was easy for me to run some code to go and pick those all out from the mock data. So I did that a while ago, and it's just sitting there, but it's not generally public, but if anybody wants it, they can have it. We're also working on developing some models of the cosmological potentials around these galaxies that are time dependent or not, that are a better representation for people to test things out on. And those are coming soon that people might be interested in. There's definitely a challenge for smaller collaborations of simulators to get all of this stuff out the door publicly, because it takes dedicated space somewhere and somebody to manage it. That's a lot easier for larger collaborations, just like for Sloan, for example, they have external funding. That's why they're called the Sloan Digital Sky Survey. Most of us don't have that kind of stuff. So yeah, and part of what we determined to release publicly depends on community input. So if we get a lot of questions about something, it's more likely that we'll try to make it available.
We have a couple more minutes in case we want to raise any other topics or follow up on these. Go ahead, Anna.
Yeah, I kind of wanted to follow up on this and kind of saying, can we get there? Like, how do we get more funding for simulations? And is this something that you think would be worth even doing, or do you think this sort of the current framework kind of has more mileage? And that's the question to, I guess, all of the different simulators.
This is something that we also discussed on one of the breakouts. It wasn't specific to simulations, but yes, getting stuff out of this meeting that will help us procure funding. But for that, we also have to decide on funding priorities, I guess.
I see that that's like an interesting like connection. Like in the chat, people are saying that there is a buy-in to SSS. That might be an interesting model for simulations, maybe.
Oh, sure.
Selling tickets to an Anki-Mox.
Yes, in the.
I hope we don't have to do that. We're pretty desperate at that point. I will say, I want to shout out, and I think this is true of most simulators that do big stuff. The national computing resources have been extremely supportive on a very deep level to a lot of our simulation collaborations. Since a collaboration like this is like a super user of something like Stampede or the other resources that have come online recently, we actually meet with the people that direct those centers personally and know them and talk to them offline about how best to do it. And the support that they've given us is really above and beyond, I would say. And I think it's really worth acknowledging that. And of course, we try to in our paper acknowledgements, but I just want to give a shout out because I think it's really important to acknowledge that there is like national funding here in the US, for example, national support for this kind of computational resources that's made a lot of this possible. Otherwise, for instance, we wouldn't, if it weren't for the grace of the people down at the Texas Advanced Computing Center, we wouldn't have any place to store all our data. If we weren't engaged with Flatiron, we wouldn't have a place to back it up.
Okay, so perhaps any last minute thoughts, a couple last straggling points that anyone wants to raise? Okay, I think we have worn you out successfully. So perhaps we can move on to Anna, who's going to officiate the closing ceremony.
Did you want me to share it, Anna, or you?
Yeah, you can share it. That will be great.
Yes.
There's some graphic stuff. Anyway, well, just to start, thank you all for coming. This was such a huge experiment. Like we, try to think through kind of how this might work, but we didn't. Oh, you're on what's next slide, Adrian.
Oh,
but
thanks.
Yes, we are all wondering. But anyway, yeah, we're really, not sure because there are like so many new aspects of this meeting. So thank you all for sticking around. It's been a lot of fun for us. I hope it was for you. And so in the next few minutes, we just sort of wanted to reflect on what we've accomplished this week. So the next slide, you see that there were 63 submitted talks for a total of 420 minutes. And as we learned, you can listen to talks at speed 1.25, 1.5, and even 2. So this we might be past the point of no return. I feel like it will be really difficult to go back to listening talks in real time after, yeah, saving a factor of 2 on talks. There's been huge engagement on Slack. We had 161 Slack members and over 3,000 Slack messages. There are still only 99 intro slides. I had fun reading about people's lack of travel, but substituting it with cooking. There's a surprising amount of crafting. I was, particularly glad to see that. So it really was nice to see the intro slide. So if you want, there's still time to add your own if you haven't already. Kind of more tangible interactions. We had 62 pages of running notes. So we are hoping that, well, first of all, thank you all so much for contributing. It's been really amazing whenever we even go to the random breakout rooms, like someone starts and like puts the list of the names of people in it and start taking the notes. This has been like an awesome record-keeping mechanism. What we are hoping that this might turn into would be something like a 5-page white paper where we summarize our findings and present them to the community. So if you would like to get involved, please get in touch with the SOC. And finally, I wanted to kind of talk a little bit about the demographics we've had. It was, well, first of all, way more people than we expected to get. And I think we've kind of mentioned that many times over. And so the breakout was between the registered participants. We had 70 students, 50 postdocs, and 80 faculty. But for the talk submissions, it turns out like they were all actually pretty equal. So it was really nice to hear such diversity of talks on just listening on Dropbox and also engaging on Slack. It's really been a kind of around the globe effort. We had people from, I guess the time zones were most friendly to Europe and East Coast of the US. So that's where most people were coming in from. But shout out to people on the West Coast waking up the entire week, and also some people in the Pacific time zones, who maybe not participating during the live meetings were really very active on Slack. So this has really been awesome being able to see all of you participate here. And finally, I guess we teased it at the beginning of today. We really did not expect like this to remain the attendance, especially for today. We suspected, like, since it's going to be more of a hands-on and what do we do next kind of day, it is very encouraging that we managed to hold your interest during the entire week. So thank you all for being here. We at least had a lot of fun. Thank you all for filling out the feedback form. We are, happy to hear feedback, think of how we can do better. But for now, and I guess as you have seen during like this morning's introduction, the moderators deserve like a huge thanks. And we've been having them, thanking them sort of as we were going along every day, but they went above and beyond and deserve some little extra. So we are having some awards for our great moderators. And the first award is on in the spirit of the Dundies for who have seen The Office. So the first award goes to Tim Lee and Guillaume Thomas, who I think did not really know what they were getting into when they said yes to moderating the first day. So it really was a journey into the unknown, and they did well and gave us such a great tone to the meeting. So Ting, Guillaume, thank you so much. And Jason will be presenting the next award.
Yeah, so the second award, they had an epic 140 minutes worth of video to watch, which I think was more than any of the other moderators. And so we'd like to give the binge watching awards to Alice Deason and Mike Peterson, the day 2 moderators. Thanks very much to you both. You did an excellent job.
So the next award goes to Dennis Urkel and Robin Sanderson, who had, if you will, the most controversial topic. So we're giving you the Falsifiability Award. Thanks, Dennis and Robin.
And then lastly, for the moderators, so covering a huge range from the Milky Way's accretion history all the way out to many megaparsecs in distance, we have the Dynamical Range Award for Shani Danieli and Chutska Starkenberg. And then one final very important award, Abigail, I hope just joined. I can't actually see the participants right now, but the Most Valuable Organizer Award goes to Abigail Cream, who's an employee at the Flatiron Institute, part of the Simons Foundation, and without whom none of this would have happened, because she and her team made it possible for everyone to upload their talks and set up the Indico page and really helped everything go incredibly smoothly on the technical backend. So let's all thank Abigail. Okay, so now the big question, which is I think we've spurred a lot of discussion this meeting. I've had so much fun, as Anna mentioned. I think we all have on the organizing side. So I hope you've felt some of that momentum as well. Where is it? So the big question is what comes next? Do we have streams 22? Is that the next interface here? Or do we want to try to have some follow-up discussions and meetings to keep what some of the things that have been raised throughout this week going on a more hands-on way? So there's been some suggestions and discussions or comments throughout the week implying that it might be useful to have some shorter sort of focused follow-on meetings or over the next year or 6 months or so to sort of fill the gap until the next larger Streams 22 meeting. We're very happy to help facilitate that kind of thing, and I would like to join such meetings. I would love that. You should all feel empowered to organize and advertise these things. We will help you broadcast that out. I think one great outcome would be to set up a sort of informal set of working groups on different topics, some of which came up even in the last hour or two. And I made a section in the running notes all the way at the bottom in the key takeaways. I don't remember what I called it, key something, where we can start listing what maybe some working groups would organize around. One, for example, would be around an open streams database or implementation of using AstroCats for collecting and sharing stream data. So let's think about this. I think we're not going to take on the full organization, but we're happy to facilitate. So please get in touch if you're interested in doing something like that. Anna, back to you.
Yes. So finally, if you have found this workshop useful, and if there are some papers that come out of it, we'd like to hear it. There certainly hasn't been any shortage of ideas for great projects on sort of all levels, both organizational and just pure scientific papers. So if you end up using anything that transpired from this week, please consider publishing like or the statement and acknowledging the workshop. And yes, I think Robin is asking if we can we'll put this statement on the workshop website, so it will be available. And with that, thank you all. This is our conference photo. Thank you all so much for being here. And yeah, hope it's not too long since we meet again in this format.